Okay, so welcome back. And the second speaker of this morning session is Professor Lingyun from Tsinghua. And he's going to talk about the multi-pollutant traceability via dynamic CGO solutions. So let us welcome Professor Lingyun.
Thank you. Thank you for the introduction. Uh, it's my great honor to be here to talk about our recent work. So you see, the topic here is like the water pollution traceability via some special functions. And this is a joint work with Professor Zhongjing Wang and Professor Hui Yu and my PhD student Shenwen Yu. And so, okay, so um, basically, I really want to talk about the multi-pollutant case, but I decided to divide it into two parts because it's originally come from the single pollutant case. So I'm going to talk about this part first, and then I will highlight the difference between the multiple pollutant part case and the single case. Okay, and so this problem actually comes from the Department of Hydraulic Engineering. Professor Zhongjing Wang is a professor in their department. This is a joint work with them, and the motivation here is we want to check those type of pollutions in the water bodies like river and lake, and also the large part like the ocean. So we have different kind of waste, those sources of the pollutant into the water, like the domestical and the industrial and the agricultural waste, all kinds of. So we really care about the multiple pollutant case. And we start from the single one, and we want to build a simple model for the single pollutant case and generalize it to the multiple one. So for the single pollutant case, the governing equation we consider here is try to include the different type of things like the diffusion and the convection and the reaction. So because this is a single one, so the reaction only happens with the pollutant with itself. Okay. So now we have this equation, and to be more realistic, those coefficients should be variable. But I talk with them. The very important thing when we do applied math is talk to the people who really work on those situations. And we talk to them, and we try to formulate some real assumptions here. And they told us that we are talking about a very large scale problem, that we can do something like the averaging. So when we talk about averaging, those small scale stuff disappears. Then we can end up with this simple equation with constant coefficient. That's our starting point. So with those type of constant coefficients. So this is the governing equation. We have the domain here is the gamma, is omega, and the total measurement time is from 0 to t. And W here is contaminant concentration function. That's the solution of this equation. And also we have the diffusion and the convection and the reaction coefficient, constant functions. And F here is the sources to be determined. We want to reconstruct F from some information of this measurement of the contaminant concentration. It's partial data. We cannot measure it everywhere. Okay. But this one is not that simple enough. We try to, since we take the advantage, we assume they are constant coefficients, so we can use those type of the Liouville type transformation to make our problem simpler. So now we can apply those type of transformation here. We apply to the previous one. So this is the whole governor equation here. We have different types. Now we can apply this Liouville type of transformation, we end up with very simple equation. That's Hiti equation. Everybody familiar with this Hiti equation? Okay, so now the governing equation is a forward problem. I'm talking about the inverse problem, so we need to define the forward problem first. So the forward problem is like this. We have very simple Hiti equation, and so the given forward problems, formulation for the forward problem is the following. So given those constant, now we only have one kappa left. So given kappa and F here stand for the contaminant, the pollution sources. And for the forward problem, given kappa and f, we try to solve this heat equation and get our measurement. The measured data is here. It's just a partial data. It's a boundary measurement. So the inverse problem is inverse boundary problem. So once we have this forward problem, so the inverse problem is well defined. So we try to reconstruct the right-hand side, which characterize the source, the pollutant sources. Okay, we try to reconstruct fxt from our boundary measurement phi xt, which is u over the boundary. That's the inverse problem. But if you kind of interested in the inverse problem, you must read the most famous book, Inverse Problem for PDE by Viktor Isakov. And when you turn to chapter, I believe it's chapter 1, the first pages of chapter 1, you will find out that those type of inverse boundary problem for heat equations is very imposed. And we do not even have a uniqueness for those type of problems. That's very easy to check. Think about u here is a given for any compact supported function u. Assume u is just a compact supported. For both spatial variable x and time variable t, u is compact supported. Then you apply this operator to u, then you end up with f, which is also a compact supported, is not zero, non-zero, compact supported function. And the boundary measurement for u is 0. So how can you recover f from the zero boundary measurement? So there is no uniqueness. So for any compact supported function here, we can assume, we can see that is in the kernel of our inverse problems, that there is no hope to build some uniqueness. So we must assume something for the right-hand side term. Okay, so again, to do some applied science, to do some applied math, we need to turn to the people who really work on that field and talk to them, try to make some reasonable and realistic assumption on something we want to reconstruct. So basically here, we assume the following answers for the right-hand side. So you see, we use f, the right-hand side of this heat equation, to characterize, the pollutant sources. So it's reasonable to assume that those are the point sources. Okay, we only have a finite number of points which has the support of those sources of the pollutant. So then we can use drag delta for the spatial variable, and then for each source position, for each source location SG, we assume we have a function only depend on time associated with that source location. That's basically our time-dependent source intensity for that point. This is a very strong, mathematically this is a very strong assumption, but in practice it's reasonable. So we can assume something like that. With those type of condition, we can eliminate that non-uniqueness. So we can prove the uniqueness, we can prove the stability, at least for the single case. For the single pollutant case, we can prove the stability. So this is very strong, mathematically it's a very strong condition, but it's reasonable, okay? And the second one is quite mathematical, is assume those are the distinct positions and that function, that the intensity functions belongs to some not that bad function space, L2 here, okay? And also another realistic assumption for those positions, especially for the intensity function, is we need to assume there is a inactivation time or silent time. That's basically our total measurement time is from 0 to capital T, and we assume there exists a T star, which belongs to 0 to T. After that silence time, all those GT will be 0. Okay, that's basically the assumption on those functions, on those L2 functions, intensity functions. Okay, with those assumptions, there is hope we can reconstruct those right-hand side, the sources. Okay, so this is a very typical inverse problem. For those type of inverse problem, we have the following method to deal with that. Okay, the first one is a very popular one, a joint stream method. So basically, that means we have our forward problem. We have fx equals to y. X is input, y is output. Y basically our measured data. We formulate the forward problem, and then we can formulate the inverse problem as a data matching problem. So basically, you're try to minimize you define a distance function. Let's see. For example, fx minus y, and takes L2 norm of that, take square, right? Then, so you assume this is your data misfit. That measures how different your data and the recorded data, how different they are. Okay, and then you apply some optimization techniques to minimize this guy. And when you do that, you find out the very efficient one to solve that problem is a joint state method. That's where this a joint state method comes from. So basically, we need to solve a least squares problem. Usually, it's a U-post problem, then we need some regularization. So we end up with regularized least squares problem. Okay, that's a very popular approach. And the third one is the direct sampling method. It is also very popular for the inverse problems. And it is that famous for it should be fast. Usually it's fast, but not that accurate. So usually you get a fuzzy one, but it's fast. For this direct sampling method, you usually need the fundamental solution of that Gavin equations, which is a heat equation here. And we're gonna talk the second one. We're gonna focus on the second one. We will not talk about the sampling method because usually it cannot give us a very accurate result. Okay. And the second one is closely related to the first one, actually, because a joint state method originally comes from, as far as I know, comes from the control theory. So we look into that, and we generalize something. We will see the detail later. And basically, we start from the rational form of this problem and use the so-called complex geometrical optics solution and to build some test functions and use some boundary control methods to build some identity and then make use them to build some functional we can minimize. That's basically the approach we're going to talk about. So it's mainly focused on the boundary control method plus CGO solution. Okay. So let's start with recast the inverse problem using the rational form, using those test functions. So basically we multiply, this is our equation. This is a simple one. We have a simple form that we can make use of that. So this is a heat equation. We multiply both sides by this test function v. We're gonna talk about what type of test function we're gonna use. Okay, we multiply this section both sides by this test function v and do integration. And let's look at the right hand side. So if we choose those test function properly, see, we assume V forms a very good basis of the whole space, of the space and time, space plus time, okay? Then the right-hand side will be a projection of our unknown, of fxt, to those bases, okay? You have a good basis. If you know the projection of some function to those bases, then you can easily reconstruct your function. So that's basically the idea. So we want to get the value of this projection to these spaces. Okay, that's the idea. Okay, we know that one equals to the left-hand side. So let's look at the left-hand side. So basically, we do integration by parts. Okay. Okay. So for the left-hand side part, before that, I'm going to talk about this Q minus is the whole domain times from 0 to silence time. And the sigma minus is just the boundary where you have the receivers. The boundary times from 0 to silence time. And the Q plus is the whole domain times from silence time to the end of the time. Okay? And the same thing for the sigma plus. Okay. And now we're going to put some assumptions on the test functions. We don't need too many test functions. Okay, we can put some assumptions on those test functions. So first thing we're going to talk about is the equation, the adjoint equation, so which is similar to the joint state method. We need to assume our test function satisfy some type of adjoint equation with respect to the original equation. Okay, because after the integration by parts, we can move this operator on top of v. Okay, that's the idea. Okay, so if we assume v satisfies this adjoint state equation, and then we do integration by parts, we move this operator on v, that's equal to 0, and we can drop that term and only the boundary terms left. Okay, only the boundary terms left. This is the spatial boundary term, and this is the time boundary term. And for the time boundary term, because the original state for u is 0, then we do not have the 0 term. We only have the t star, the silent time term. Okay, that's basically how we derive this identity. Okay. So again, we can define the random height side equals to RV. Basically, this is a projection of our unknown to the one of the basis function, V. Okay, this is RV. It's definition of RV. And let's look at this RV. We know from the previous one, we know that this guy equals to this this formula. We need to calculate the boundary integration of our data phi and the test function. Okay, but the test function, since we design those test functions, then we know the value of those test functions everywhere. There is no problem to evaluate v. Okay, and phi here is our data. So that's the recorded data. Of course, we know what it is. Then we can evaluate this boundary integration. But the thing here is we do not have any knowledge of this concentration U, the solution to that heat equation everywhere. Okay, the first integral is over the whole domain. So we do not have any knowledge of this U at some particular time and that silent time everywhere. If we can measure it everywhere, then we can find out where they do the emission. Okay, so now we need to deal with how to evaluate this integration over the whole domain without the information ux t star, without to measure the information of u everywhere. Okay, that's the problem we're gonna deal with. So the solution here is using boundary control method. We're gonna evaluate that integral. Recall here that we do not need to know u everywhere, but we can find a way to evaluate this integral. Okay. We use the boundary control method. We can prove the following lemma. Before that, we can give a notation of the function spaces, function set we use for the test functions. So basically, that's very, very simple. Because again, we have the constant coefficient, then we can use this advantage. We can build this so-called CGO, we call it dynamic CGO solutions. So it's an explicit complex solution to that heat equation. Okay, so we can build a function space like this. We're gonna use this H as our test functions. Okay, and with this, then we can prove the following lemma. For each test function V belongs to that space, there exists a corresponding boundary control. You see, omega here belongs to a boundary control. It's a boundary function. Okay, so there exists a corresponding boundary control omega such that this integral over some missing information here, actually we can build an identity that's equals to a boundary integration. But this boundary, the integrand is something related to our measured data phi, and also the test function itself, and the diffusion coefficient, and also our boundary control. Okay. So this is the kind of the exact boundary control. If you talk to the control theory guy. Okay. Usually for the heat equation, we cannot prove the exactly boundary control controllability, but here we can because we choose some very particular functions. Those type of functions, they are smooth functions. Okay, so we have very good regularities and we can prove the exact controllability Just a short remark here. This lemma only gives us the uniqueness, so only gives us the existence, so we can find one boundary control such that this identity holds. But how to find it? So we need to, because we're gonna to do real calculation. When the data comes in, we need to run some calculation and I'll tell them that where the source location, where those pollutant is. So we need to do the calculation. Fortunately, we have well-established method to solve for this boundary control omega. That's a very famous Hilbert uniqueness method. You see the name of Hilbert. Okay. So it must be a very famous one. Okay, so the so-called Hilbert uniqueness method to really do the calculation and find out, numerically find this omega. We will go back to that method again. Okay, and before that, let's talk about the uniqueness and the stability proof. So now we have the forward problem. We have a new forward operator. Because the thing here is, before, the forward problem is for given sources, for the location and the intensity functions. For given sources, the forward map will send it to the measured data. It's a boundary measured data. Is a function defined over omega times the time domain 0 to t. Okay, that's a boundary measurement. But now we decide to project using those boundary measurement to some spaces. So now our data becomes RV. And V is belong to some very special function spaces. So now we have a new operator. We have less data than before. Once you have the boundary measurement, you design V, then you can get RV using the previous one. But of course, we have less data. With those type of RV, can we reconstruct? Do we still have the uniqueness for the inverse problem? That's the first problem we're gonna to answer. So the answer is a positive. Yes, we do have a uniqueness. The forward map is injective. Okay, so this forward, it's not a linear one. It's not a linear one, but we still can prove it's injective. And also, this is a direct result of this stability. So we can prove, actually, we can prove the following stability result. We have a Lipschitz type stability. So basically, once we have our boundary measurement, then we can build RV. If you have two RV, they are quite close, then we can build this Lipschitz type of inequality. They can control the distance between two set of parameters. Those are the parameters like the source locations and the intensity functions. We can build those type of Lipschitz type stability. And also the stability constant, we can have an explicit formula for the stability constant. So you can see M here is the number of the non-zero sources. Of course, it's increasing with respect to M. And also, sorry. And the data here is the smallest distance between two distinct sources. So roughly speaking, when you have two sources, they are very close to each other, then it's quite hard to reconstruct them. Okay, that makes sense. That's reasonable. After we got the uniqueness and existence and the uniqueness injectivity, then we turn to how to design an efficient algorithm, how to numerically reconstruct those things. So the idea here is we borrow some idea from the computer science. Is we divide it into the whole computation into different phases. Like, let's see, offline part and the online part. So why are we gonna do that? Let's first talk about what is our offline computation and what is online computation. Okay. So offline computation phase is kind of you need to do some preparation. So the main thing here is it's independent of measured data. So you see, you know, when we solve the real inverse problem, it's usually very large scale problems. Think about like medical imaging. If you want to talk about the high resolution medical imaging or maybe seismic imaging, seismic inversion, you need to have a cluster, especially for the seismic one. You need to have like 天河, like 太湖之光. So you need to have a very large cluster, and then you can use their computational power to solve those problems. The main thing here is for each iteration, you basically need to solve many, usually thousands of PDE. So you need to have very efficient PDE solver, and you need to have very good computer and solve that for you. Okay, so once you have the data, you solve PDE for that, and you solve that inverse problem intuitively. But here we divide the whole computational phase into the offline and online part. So for the offline part, that means you do not have any measurement, any measured data. What you know is the formulation of this problem. You know the diffusion coefficient, you know the convection coefficient, you know those other type of constant coefficient behind those terms, and you know the formulation, you know that's gonna be a heat equation you're gonna solve, and you know the domain, the shape of the domain, you know which lake, which river, which ocean. That's basically the knowledge you know, but you do not have measured data. In this case, in this phase, then you can, we call it offline computational phase. Okay. So for our algorithm, we got the mean computational load will be in this offline phase. So basically, we solve thousands of PDE in this phase. Okay, independent of the measured data. Okay, and once we have the measured data, so once we have those data kicks in, we call it online computational phase. That means you already have the data. Now we're gonna use the result from the offline. You use the preparation in that offline phase, and also the measured data to calculate some result, calculate the source location, and also calculate the intensity functions. That's basically belongs to online computational phase. Okay, so for the I'm gonna talk about the online phase first. So in this case, we already know the function, the tax function v, and also we know the corresponding boundary control associated with those test function v. So we know v, we know associated omega, and then once we have the measured data, we can use them to build RV. So we already know RV. And then the minimization here is quite simple. So actually we divide our online phase into two parts. The first part is use those RV to find the location and the total intensity. Total intensity means we do the integration over time. That's the total pollution amount you do the emission, when you do the emission. Okay, so the first part we're going to reconstruct the location here as, and also the total intensity. So basically assume you have 10 distinct locations. So it's a 3D problem, so you have a 3 plus 1, totally 4 numbers to characterize one location. So basically you only assume you have 10 different sources, then you only have 40 numbers to reconstruct. So this is a very small scale optimization problem for this part. It's quite easy to solve. So we can even use the global optimization techniques to solve this problem. It's quite easy. Okay. After that, so since we have the location, we fix those locations, and also we know the total intensity. That's basically, if you think about the Fourier transfer, that will be your A0. Okay. So after that, we're gonna to reconstruct the intensity functions frequency by frequency. How are we gonna do that? We choose different alpha when we build the CGO solutions. Recall that we have the CGO solution like this. So this is our CGO solution. We have several parameters we can tune here. So for alpha equal to 0, that means this CGO solution is static. It doesn't depend on time, so it's a static. Okay, then we can tune this alpha, make it time dependent, and our frequency kicks in. Okay, so if we choose alpha equals to this guy, and then we can check our projection again. This is our RV. That's basically you find out as okay, this is just a Fourier transform of that intensity function for some corresponding frequencies. So that's how we can reconstruct the intensity function frequency by frequency. Okay. So after that, if you get the projection of that intensity function into some particular frequencies, then you can easily build that, use the Fourier modes and build the intensity function. So that's basically that's the idea. Okay. Now we need to move to the offline phase. That's the very interesting part. So the first thing here is we need to solve this boundary control. For given test function, we need to find the corresponding boundary control. As I mentioned before, we have the Hilbert uniqueness method to solve that one. That's a well-established one. So let's do that. Okay, so we can define this cost function like this, and we have our regularization, the L2 regularization term, and we apply some minimization techniques to this cost function, and then we can solve for this omega. Omega will be the minimizer of this guy, and we have a uniqueness. The regularized boundary control, we do have a uniqueness result for that. But this one is only show us that for any test function, RV is computable. But to solve this minimization problem, we're going to minimize this guy and find out the minimizer omega. But to solve this one, I tried once. We need to solve like 2,000 times PDE, 2,000 times heat equation, and find a good omega for that. So that's something like we solve 2,000 heat equations for just the one boundary control. Think about we have 100. Think about if we have, let's say 100. 100. If we have 100 cost test functions, that basically means we have 200K PDE need to be solved. Heat equation need to be solved. There's a huge amount of computational cost. It's not affordable, basically. So this is only the Hilbert uniqueness method here only show us this RV is computable, but it's not a very efficient approach for that. This is a very costly approach. So for real scenario, it's not very attractive. Then we need to think about other method, other approach to solve for those boundary controls. The thing here is we have a bunch of controls we need to be solved, not just one. Okay, so before I think I never find some literature that talking about like we have a bunch of boundary controls we need to solve and how to efficiently solve that. I never find some literature. If you know, please let me know. But I never find any literature related to this one. So, but in this situation, we do have a lot of boundary controls need to be solved. Then the way to do it, I think maybe we can use something like we can call it the targeting method. So basically, we build a basis, a nice basis for those for the boundary control L2 omega, L2 sigma. So for these boundary controls, then we solve. So for each base function, we solve one heat equation. Then we know the target. And for those targets, it should form another basis for those target function space. Then we can do something like a projection to this target function space and find out the coefficient, then build the boundary control. So basically, that's the idea. So the so-called nice basis for the boundary control here we choose is as following. Because here is a 2D problem, and the boundary is just 1D, then we can use sine cosine to build the basis. Here we use just cosine for the time domain, and we use sine for for the spatial domain. Don't ask me why we choose this one, because this is the first one coming to our mind, and it works, then it is. So we didn't spend too much time to optimize this one. I think it works also for the 3D problem, then it is. Okay. After we build those target functions, so basically those are the target functions, then we can solve this very simple optimization problem on one particular time slice. So it's only depends on the spatial domain. So it's, the dimension is just a 2D dimension, it's just two-dimensional. So we can solve this minimization problem and find those coefficients and use those coefficients to build our boundary control. That's basically how we efficiently build a lot of boundary controls. So this is when it runs very fast. And here, as I mentioned before, if we use 100 test functions, we're going to solve 200K times heat equations if we use Hilbert uniqueness method. But here, since if we choose 1,000, if we choose 1,000 basis functions for that boundary control space, then we only need to solve 1,000 times heat equation. So that's basically, we gain a lot from this one, from using this this approach. Let's see some numerical experiments, and we assume the domain is 1 kilometer by 1 kilometer, and the diffusion coefficient is 1 square meters per second, and T star is 38.4 hours, and the total measurement time is 48 hours, 2 days. Okay. And the intensity function, I will draw some picture of those functions, and you can see that this is, assume we have 5 different sources, then we can do the reconstruction. And I believe the right circle means the true solution, and the blue cross means the one we the reconstructed locations. So you can see here, this guy have a little mismatch here. So if you calculate the relative error, you can see here, this one is better. Okay, if you calculate the relative error, you see the relative error of the precision reconstruction is less than 1%. And if you calculate the total intensity error and also the position error, so it's basically 2.9, less than 3%. And so as I mentioned before, we decompose the online part into 2 parts. First part, we calculate, by the way, the size of this symbol, that stands for the total intensity function. So the total intensity, okay. So the first part will reconstruct the location and also the total intensity. After that, we fix the location and total intensity, and then we reconstruct the intensity functions frequency by frequency. So this is the one we choose. So basically, we decompose the unit circle into 8 different directions, and so basically that's a frequency. We use 8 different frequencies. Because we assume our intensity function are slowly varying, so we don't need very high accurate frequency for the reconstruction. Okay, so this is the numerical result. This is the first one. So you see the right one is the true intensity function, and the blue one is the inversion result. So basically, I think the most interesting part here is we can accurately reconstruct those peaks. Okay, you see 2 peaks here. We can accurately reconstruct those things. They are very interesting in reconstruct accurately those peaks. Okay, that's corresponding to the second one. And the third one, remember this one is associated with this guy. So small reconstruction error here can lead to a very relatively large reconstruction error in the intensity functions. So this is a G3, and G4 is better, and G5. So for the single pollutant case, we can accurately reconstruct the location and also in the intensity functions. So that's basically this numerical example tells us. Okay, now we turn to the second part, the multi-pollutant case. So I will going to just highlight the difference between the multiple case and the single pollutant case. So for this one, the governing equation. Again, we're going to consider diffusion and the reaction, and also the diffusion reaction, and also convection part. Sorry, I forgot to list the convection part probably. But the convection part is the one easy to handle. So let's forget about the convection part first. So let's look at the governing equation. Before, for the single case, we have a Liouville type of transformation can transfer that kind of complicated equation into a heat equation. We want to do the same thing here. In the very beginning, we want to do the same thing here. So if we find out that if we have this kappa is a matrix value coefficient, diffusion coefficient. Okay, so this is a matrix value diffusion coefficient, and A is corresponding to the reaction. Okay, and the capital U here is the contaminant concentration. So we have L different type of pollutant. Okay, so if we have a kappa and A, kappa A equals to A kappa, then we can use the following transformation. Then it gives us a heat equation again. It's a heated system, but it's a simple, right? Okay, so this is the condition we find out. That means we have the coupling system, because the reaction means one typical pollutant will have reaction with others. Okay, so this result tells us that if we have this condition satisfied, if we can assume this guy, then we can decompose this coupling system into isolated single equations. So let's go back to the single one. So linear combination of those, we can use the linear combination. We can use the linear transformation. And then we end up with isolated new kind of pollutant. Then we can decompose this one into single ones. Then we can solve for that. Use the previous one to solve this problem. But when we do not have this identity, when kappa A is not equals to A kappa, then the transformation doesn't work. Okay, so we cannot decompose it into the previous one. And here we list some simple, sorry for this typo, some simple scenarios we can get this condition. So the first one is if all those L different pollutants, they share the same diffusion coefficient, then this kappa just equals to kappa 1 times the identity matrix. Of course, we can have kappa A equals to kappa A kappa. Okay. And the second part is A is diagonal. That means any pollutant never talks to other pollutants. The reaction only happens with itself. That's a very simple one. Okay. So with those two simple scenarios, we can have this condition satisfied. Otherwise, we do not have it. So the first interesting part here is we need to deal with this guy. We need to deal with this with these original functions, original equations. We cannot use that type of transformation to absorb this term. Okay, that's the difficulty one kind of. And for the sources, we have the very similar assumption on the right-hand side. So the answers for the right-hand side is like this. We have different source locations. For each location, we have L different intensity function corresponding to L different pollutants. Okay, that's very typical setting for the right-hand side, for the source location, for the source term. And the following are the same as before, as a single case, as a single pollutant case. Okay. And now we need to recast the whole problem using the projection technique, project to a good basis. Here again we use the CGO solution to build the basis and do the projection to those good bases. And so basically, the technique we want to use is very similar to as before. So we multiply the equation, but now we have much complicated equations. We have much more complicated system here, and we multiply this one by the test functions. The test function need to be a vector, right? It need to be a vector. So we multiply this by the test functions, and we do integration by parts. Okay. So once we do that, we need to assume that, sorry, not an assumption here. Once we multiply the test function, we multiply the equation by the test function, and then we do the integration by parts. One more step here. So we can assume kappa is invertible. That matrix is invertible. You do not have one pollutant corresponding to zero diffusion coefficient. If you have it, remove it, because it's never diffuse. Then you can remove it. Okay. So we can see kappa is invertible. It's an invertible matrix, and then we can apply some techniques from the linear algebra, and then we end up with a roll-down matrices of this guy. So we can transform that into roll-down matrices. So basically, one roll-down block here means we can group those pollutants together and form an isolated one. Okay, so we can solve one block by block. So that's basically the idea here. But the roll-down matrix is corresponding to several pollutants. We cannot turn them into isolated one. If we can, then we go back to the previous case. Okay. So now the system becomes like this way. Okay. So now we need to go a little bit further. We need to build something like for each block. After this, we're gonna solve one block by block. For each block, we need to build particular test functions, and then we need to build the RV for that, and we need to build a boundary control for that block, and then we can, as before, we can turn it into offline and online part and solve for the locations, and also intensity functions. Okay. Okay, I think I will not go to the detail of those derivation, but the idea here is we need to reconstruct this right-hand side step by step, because we already turned it into block by block. Okay. And this here, the difficulty too is now before we just need to, for each function, we just need to build one boundary control, then we can build RV, the projection of the right-hand side onto that basis. But now we need to build a different type of boundary control. Here, we assume the function space here is not as simple as before, because now we need to use some eigenfunctions here. So the new test functions here need to be in this space. It's corresponding to the eigenfunctions of the Laplacian. Okay. And then we can do integration by parts again. Then we get this identity associated with so this identity kind of builds the connection between the right-hand side, the projection to that basis, and the left-hand side. That's integration. The result of the integration by parts applied to the original systems. Okay. Now we have the functional RV again. Again, this is a vector valued, so this RV also becomes more complicated. And then we can prove, as similar as before, we can prove this boundary control, the existence of boundary control. Okay. So for this time, for the system, we can only prove approximate boundary controllability. It's not exact controllability as before. So now we have some new idea to prove some exact boundary controllability. So we haven't written it down. So I believe we can do it, because again, it's a smooth function. So probably we can get it. But okay. So for this theorem, we can prove that for any test function and any small constant epsilon here, we can prove that there exists a boundary control such that the distance, the difference between this identity, this integral, and this boundary integral is quite small, as small as we need. Okay, so this is approximate boundary controllability for the system. This is completely new. And the calculation of RV is a little bit different. So because now we have L different type of the pollutant, so we need to define a series test functions. So basically we get the first function. So we get the first test function, which is the eigenfunction of the Laplacian. When your domain is good, then you can build the explicit form of that. And then you can use the first one as the right-hand side of this equation, and then build the second one. So now you see the thing become more and more complicated. You still can calculate that, but we do not have an explicit form of that. Okay, so once we get V1, we can put it into the right-hand side, and we solve it. It's more like a Helmholtz equation. Yeah, we can solve it for V2 and put it here, we get V3, and so on. Okay, and once we got all those type test functions, we can multiply original function and build that identity using those type of test functions, and then we can build RV. So this is the identity we build RV. Okay, now let's go back to this one. So we can check it term by term. The first one, we can derive that when using, we can evaluate that when using boundary measured data. And the second term, we can evaluate this guy using the boundary control functions and the boundary measurement. And the third one is 0. So basically it's just is equal to 0. So this is how we build RV for the system once we have the multipollutant. Okay, and the uniqueness theorem, the result here is, again, we try to prove some, we haven't successfully proved the stability, but we can prove the uniqueness. That means we can, the measured data, the boundary measured data can determine the locations and the total intensities, and also the intensity function. That's the uniqueness theorem we can prove. So basically, the result is we can, as I said before, so those boundary measurement data, we can use that to build RV, and the RV can uniquely determine the locations and the intensity function. That's the uniqueness theorem we can prove. I think I need to skip the detailed proof of this part. It's very okay. And the reconstruction, as I mentioned before, I'm going to highlight the differences between the single pollutant case and multiple pollutant case. So the difference between those two cases with respect to the reconstruction algorithm is as following. So for the first step, it's quite similar. We assume we have we have 10 different source locations, but now we have 5 different type of pollutants. Then we have 5 times 10, 5 times 4. So we just have a little bit more, but still quite a small scale problem to be optimized. So this is the minimization problem we're going to need to be solved for those locations and also for the total intensities. And for the second part, it's quite similar to before. We need to solve the intensity functions frequency by frequency. So this is the way to solve it. So basically, we can use alpha k equals to this guy, and to build the test functions, we need to solve several eigenvalue problems and find the first test function and use that one as the right-hand side to solve for other test function one by one. And after we get those test functions, we can build RV. And then we can solve this small-scale optimization problem to find the locations. And we can find the intensifying functions of frequency by frequency. Once we have those projections, then we can use the Fourier modes and build them, the build intensity function to just glue them together, then we can have those intensity functions. So it's basically that's the idea. And also for the boundary control. For the boundary control, we use if we use the Hilbert uniqueness method, that tells us those RV are computable. Again, the Hilbert uniqueness method tells us even for system we can compute those boundary controls and we can compute RV. And a more attractive approach is like this. Again, we can build the same basis function, the same basis. So no matter you have a single pollutant or multiple pollutant, you can use the same basis for the boundary control. The boundary control are the same, right? The boundary control are lived in the same space, in the same function space. Then we can use this sine cosine to build a nice basis for those boundary controls. And as before, we can solve just the 2,000 times the heat equation solver, and then we can find the projection to those controls and use those coefficient to build that boundary control. That's basically the idea here. Even for the multiple pollutant case, we can do the same thing and get the boundary control here. Then we can build RV and apply the previous algorithm for that. Some other things that we're still working on. So the first thing is we try to improve the accuracy of the boundary control calculation. Now we can get the accuracy around 10 to power -4 or 5. And we try to improve that. At least we want to get it at least for the 10 to power -8. That would be good enough, I think. And also we want to perform some analysis. We already got the uniqueness and the stability for the single pollutant case. We get the uniqueness result for the multiple pollutant case. We want to perform the similar analysis for the system with variable diffusion, convection, and reaction coefficients. That's very complicated. We need to work on that. The first step is we need to prove some unique continuation result for the system. That's something we are working on. And also, we are working on the fractional derivative or more general PDEs to describe those type of fractional diffusion. That's more realistic. That's basically some future works we are working on now. Okay, that's basically my talk. Okay, thank you.
So is there any question?
Some people say that that one is more realistic, but I haven't found any very solid example to demonstrate that. Yeah. Yeah, I always heard that if you attend to some conference talking about the fractional, it's a hot topic, but I never find some solid example in engineering side. Yeah, so I try very hard to find one scenario that the only way to simulate that scenario accurately is to use fractional derivative. But I haven't found it yet. Yeah.
So is there any other question? So maybe I have a question. So I noticed that in your algorithm, you need to solve several optimization problems. So I'm wondering how difficult to solve these problems. Do they have unique minimizers? And I suppose if you convert to a wrong minimizer, if there are multiple minimizers, then you will have a problem, right?
Yeah, that's a very nice question. Actually, if we use this Hilbert uniqueness method, so this is Leon's. I think this is from the Leon's paper. And if you use the Hilbert uniqueness method, then for this function, we do have the uniqueness for the minimizer, because we have a regularization term here. So the regularized solution, we have the uniqueness result for that. But if we solve this one, a more attractive approach, this is only lives in L2. And this is relatively very simple to solve, because in this case, you don't have to solve this heat equations, no time involved, right? So this one is quite easy to solve, but the thing is we do not have any uniqueness result for that. So we can, actually I tried, so we can find several minimizers of this functional. So any minimizer will give us the, I believe they give the same boundary control, they give the same RV. So that's the only thing we need. We only need to evaluate the number. We do not care about what type of boundary control we need. Okay.
Okay, thank you. So is there any other question? So if there's no other question, let's thank our speaker again.